this is your lesson for 5.5 linearization and differentials. In this lesson, this does have quite a bit in it, but there's a lot that is not on the AP exam, so I am going to be skipping around a bit as we move through the different questions for this section. So this statement here, what makes the tangent line so important mathematically is that it provides us a useful representation of the curve itself if we stay close enough to the point of tangency. And this is where the idea of locally linear comes from. So whenever you zoom in on these continuous functions, what you're zooming in on, no matter what it looks like whenever you're zoomed out at a normal window representation, when you zoom in, everything is going to look like a line. And that's the idea of being locally linear. So linearization is actually going to give you the equation of the line whenever we do zoom in at that point of tangency. And that brings us to our linearization formula. This does appear on the AP exam, so this is one that you will want to commit to memory. It's basically just the slope formula. It's just that we use L of x instead of y, but it's still, you have your y1, you have your m, which is your slope, that's your f prime of a, and then you have your x minus x1, that's going to be x minus a. So you're taking a and plugging it into the function. So a, f of a is going to be your x1, y1, and then f prime at a is going to be the slope of the line. So this is basically, again, the same as point slope form that we've been using all along in this textbook and that you learned way back in Algebra 1. So this is the linearization, and your function is going to be approximately equal to the linearization whenever you are close to where a actually occurs. So if you move farther away from a, then the f of x and the L of x are not going to be equal. But if you're close to where that center is, where x and a are going to be the same value, it is going to equal out to be pretty much the same thing. That brings us to example 1. It says find the linearization of f of x equals the square root of 1 plus x at x equals 0. And we are going to use it to approximate the square root of 1.02 without a calculator. Then we're actually going to look at the calculator approximation to figure out how accurate this is. So first thing you want to do is you want to plug in the value into the function. So 0 is going to be like my a value. F of 0 is going to give us 1 because the square root of 1 plus 0 is 1. So that's the first thing that we have to do here. The next thing that we have to do is actually find the derivative. And so our derivative here is going to be 1/2 1 plus x to the negative 1/2 power. And then I have to plug in my a value. So I'm plugging in 0 again. I'm going to have 1 plus 0, which is 1, to the negative 1/2 power. So that's basically 1 over that square root. And that's going to be 1, but you do have the 1/2 out in front. So that's going to equal 1/2. So our linearization formula is equal to the function value, which is 1, plus the slope times x minus the a value, which is 0. So that simplifies to 1 plus 1/2 x. So 1 plus 1/2 x is actually going to approximate anything that is very close to this center of 0. So if we are using that to approximate the square root of 1.02, you really have to think about this as 1 plus 0.02, because notice the formula is 1 plus x. So our x value here that we would be plugging in is actually 0.02. You can't just plug in the 1.02. 1.02 is actually very far away from 0, so that most likely would not give us a good approximation. It makes more sense that 0.02 is what we're plugging in, because that's very close to 0. So L of 0.02 is going to be 1 plus half of 0.02. Well, half of 0.02 is 0.01. So our approximation here is 1.01. Now, if you look at the actual value of the square root of 1.02, that is 1.009950494. So if we figure out how close our error is, that's going to be the actual, or the absolute value of the actual value minus what we got as an approximation. And that's going to be about 4.05 times 10 to the negative fifth. So our error is actually less than 10 to the negative fourth for this. That's a very good approximation. That's an excellent approximation, especially if you needed to find a square root and you didn't have a calculator available to find that for you. Now, the farther you move away from zero, obviously, the less accurate this is going to be. But for what we have right here, again, this is a very good approximation. Okay, so this one, we're finding the linearization of, this is just cosine of x at x equals pi over 2, and then we're going to approximate the cosine of 1.75 without a calculator. Then we're going to go back and use our calculator to determine the accuracy. So, first thing, we need to plug in the pi over 2 because it doesn't tell us what the y-coordinate is. So the cosine of pi over 2 is 0. So pi over 2 is going to be like my a, 0 is going to be my f of a value. Then I have to find my f prime value. So f prime of cosine is going to be negative sine, and then I'm approximating that at pi over 2. Well, the sine of pi over 2 is negative 1, is positive 1, and then you have the negative out in front, that's where we get the negative 1. So that's going to be like our f prime of a value. So our linearization formula is my f of a value, which is 0, plus the slope times x minus the a value. And so that is going to simplify to negative x plus pi over 2. So now, the cosine of 1.75 is going to be my x value. So I simply plug this in. So I'm finding the linearization of 1.75. So that's negative 1.75 plus pi over 2. And again, this one might not be the best example of this because you would actually need a calculator if you wanted to figure out what this exact value was. But unless it states otherwise, you can actually leave your answer in this format. And then when we look at our error, I take the actual value of the cosine of 1.75, which is negative 0.1782460,556, and you can check that with a calculator. And then we subtract from that the negative 1.75 plus pi over 2. And our error actually ends up equaling 9.57 times 10 to the negative fourth. So that means that the error is less than 10 to the negative third. So this one isn't as accurate as the previous one, but it's still very, very good. This is a very good approximation here. The next thing is more of a strategy to use. It's not necessarily something that you're going to see a ton, but I did want to take a look at this because this has some interesting, just some interesting things going on with it. So in general, if you have something that is 1 plus your x to the k value, the linearization formula is 1 plus k of x. Now x doesn't necessarily just have to be the positive version of x, it's whatever's in that format. So that's something to keep in mind here. So for part A, I have to rewrite this as a set of parentheses to a power. So this is 1 minus x to the 1/3 power, which means that my linearization, and this should be That's going to be your squiggly things. Notice it says when x is approximately 0 for this. So this isn't going to work whenever you move farther away from 0. So my linearization formula for this is going to be 1 plus my k value, which is your exponent, times my x value, which is negative x. So that's going to be 1 minus 1/3 x. So that would actually, if I'm close to 0, that is going to be your linear approximation for that problem. For the next one, for part B, this is 1 minus x to the negative 1 power. So again, my linearization is going to equal 1 plus my exponent times my x value. And so that's actually just going to be 1 plus x. Now your book does go through a part C and a part D for this. So if you're interested, you can look through that and see how the C and D work. Again, this is just something that's kind of neat that it has this type of relationship, but we aren't really going to be using it a whole lot in class. When there's a C and D, I'm actually going to skip over those. These are two other questions I'm going to skip over. This is doing your linearizations by looking at either the closest perfect square, the closest perfect cube, depending on if you have a square root or a cube root. Using the same type of formula we did for linearization, I'm going to skip those for right now. And then we're going to talk about differentials. So your differential is your differential d of x is an independent variable. Your differential dy is given as the following. So dy is equal to f prime of x times d of x. So normally we write that dy dx is equal to f prime of x. So this is actually separating this term, multiplying both sides by your d of x, and making dy equal to some value on its own. This is going to come up a little bit later on whenever we look at splitting terms and having dy and dx equal to two separate things. So this is kind of getting you ready for that. This section might not make a whole lot of sense on its own right now, but I think it'll come together a little bit later on. And I'm sure the book has a better explanation for this than what I'm about to give you. But this is important. This key value, the fact that dy, so if you're asked to find the differential dy, that is going to be your f prime of x times d of x. And we are actually going to be looking at problems where d of x is a value, so you will be plugging in and finding a value for your problem. Okay, so example 6, and notice this did skip around a little bit. There's some things I did not put in here that they do cover in the textbook. Find the differential and evaluate dy for the given values of x and d of x. So we're going to find the differential as a formula first, and then we're going to plug in the x and the d of x, and we're going to find a value. So we're going to find the differential, and then we are going to find the value. So to find the differential, you do have to take the derivative of your y formula. So the derivative, and I'm actually going to call that, if I follow along with the same thing that we had in the formula, I'm going to call that my f prime of x. That is going to be equal to 5x to the 4th plus 37 for this particular example. So my dy is 5x to the 4th plus 37, and then dx. So that is the differential as a formula. Then we evaluate. And when we evaluate, it tells me that the x is 1, and the dx is 0.01. And when you go through and multiply that, you end up with 0.42. So given the conditions that they did, the fact that x was 1 and dx is 0.01, your dy is equal to 0.42. For part B, my f prime, the derivative of sine of 3x, Again, I have to use the chain rule, so I take the derivative of the side, then I take the derivative of the inside. So that's going to be 3 cosine of 3x. So my differential as a formula is 3 cosine of 3x times dx. And then I plug everything in. So I'm plugging in pi for the x. So 3 times cosine of 3 pi. And then my dx is negative 0.02. And that gives me 0.06 for my dy. This is just some more stuff about the differential. So we do call the dy or the df, we do call that the differential. So this is something that you may see occasionally. And then this is the last thing that we're going to look at. We're finding the differentials. So you're basically doing the same thing. They just don't give you the dy equals part. But you're still doing everything exactly the same way. So with this one, you do need to be aware of anytime you take the derivative of an x, you're going to get a dx. So that's something kind of goes where implicit differentiation went. So if I'm taking the derivative of tangent of 2x and I'm looking at the differentials, first I have to look at the derivative of the tangent, which is going to be secant squared of 2x. Then I have to look at the derivative of the 2x on the inside. So that's the derivative of the 2x. So I have the secant squared of 2x. Well, the derivative of 2x is going to be 2 d of x. Because the derivative of 2x is 2, and then you have an x there, so you have to put a dx. So my overall differential is going to be 2 secant squared of 2x dx. And we're going to have to do the same thing with the next one. You'll see that we actually get differentials in a couple of these. I do have to do the quotient rule for this one. And then the chain rule comes up because of implicit differentiation, because I do have to take the derivatives of the x's. So this is going to be low d high. So the derivative of x, which is just 1 dx, minus high d low. So that's the derivative of x plus 1, which actually the derivative of x plus 1 is simply going to be dx. Because the derivative of 1 is 0, so you're actually only going to be having a dx there. And then this is all over your low term squared. Now this first dx, I do have to distribute that. So I'm going to get an x dx plus a 1 dx. X times d of x is x d of x, so that's a minus x d of x. And then all over x plus 1 squared. My x d of x is add out. So I'm left with dx over x plus 1, the quantity squared. You could also write that as 1 over x plus 1 squared and then pull the dx out to the side. But in most cases, you will see the dx on top of that fraction. So that's just a little bit on linearization and differentials. Really, the linearization is the important part of this. That's what you should focus on. But I have seen the differentials crop up in maybe one occasional multiple choice or one part of one free response question. It's not going to be a huge deal if it doesn't quite make sense, but I did want to make sure I gave you guys the opportunity to be exposed to it. This is your homework assignment. This is what has already been presented to you for homework. So please go back, rewatch the video, rewatch anything that you are not sure of, watch the book videos if you get a chance for this, and reach out to me if you have any questions at all.